Hello everybody. In the last class we learnt little bit basics about an operation of BJT. In today's class we will see how BJT can be used for amplification of signals. Right. So this is the summary of what we did in the last class. If you have a BJT in the forward active mode, you need to forward bias the base and emitter junction. So if you see, this is an NPN transistor where a P type is the base and N type is the emitter. So you got to give positive voltage to the base with respect to the emitter. So this is going to be forward biased, and this junction P and N between the base and the collector, that needs to be reverse biased. That means the collector needs to be given higher voltage than the base. So what would happen is the electrons which gets from the emitter side, which comes into the base region, majority of them will be collected by the collector because of this positive voltage which is applied in the collector. Okay. Now if you see the equations which are pertaining to this particular circuit, the first and foremost is IE is equal to IB plus IC. That means the total emitter current which is coming out here will be the sum total of base current which is going here and the collector current which is coming from the collector node, right? Okay. The next equation is IC is equal to beta IB, and beta is of the order of 20 to 200. That means the collector current is multiple times the base current. Okay, it is of the order of 20 to 200 times the base current would flow into the emitter. And beta is generally a parameter which is specific to the transistor. So every manufacturer would provide what is beta, which is 20, and beta is also related to alpha by beta divided by 1 plus beta. Okay, and now alpha is nothing but an IE is equal to alpha, IC is equal to alpha times IE. So that for that relation we have alpha also, if you want to use alpha here, right? So these are the some of the basic equations which is pertaining to BJT currents in forward active mode. Okay, let's see how to use this transistor now for amplification of signals. Okay, so before that, this also we discussed in the last class. First and foremost, when we have an transistor, we need to bias the transistor for the proper operating conditions. Okay, now to do the DC analysis, so this is the equivalent DC circuit wherein this transistor is been this base emitter junction will be replaced by a diode, and you have a current source here. Now the current source current will be given by beta IB, where IB is the current flowing through this diode. Okay, through the base emitter current. Okay, this is the base emitter current. And how to compute base emitter current? Now if VB is applied, if you see, this is a ground here, so VB minus the diode voltage, which is 0.7, divided by RB will be the current which will be flowing IB, and the collector current will be beta times IB. So you can accordingly compute what would be the drop across RC when you apply a VC here, and what is VCE. So this is the DC analysis. This is AC analysis. Okay, in the AC analysis, either this or this is the equivalent circuit. AC analysis is that once you bias it, you give a small signal, say in millivolts range out here input, and then you see and during that analysis all the DC sources will be removed and grounded. Okay. So if you see here, in this case, when you apply an AC signal here, the impedance that will be seen by the small signal into the base junction will be given by R pi. Again, this R pi is a property of the transistor. Okay, so that will be given by the manufacturer. So R pi. Okay, you can a rough approximation calculation is also available, where you calculate an RE. So time being, let's assume that an R pi is the property of the transistor, and beta times of that is going to flow in the collector. So this is the small signal equivalent. Okay, this is again the same signal here, the only same figure out here. Only thing is an additional R0 has been placed here. Okay, this is known as the output resistance of the transistor. Okay, generally IC is a function of IB, and IB is a function of the signal which is applied here, right? So when you change the collector voltage, there should not be any change in the collector current, because collector current is only a function of IB. Collector current, this beta IB is a function of IB, right? So and that IB depends on the input signal. So the collector current for an ideal transistor should not change if there is a change in VCE, but for all practical BJTs, there will be a small change in collector current. Okay, and that is to reflect that change, you have R0. Okay, this is known as the output impedance of the transistor. Okay, so now if you see, when you apply a small VCE, some change in IC would happen because of this R0. Okay. So there are several amplifier configurations. The first and foremost is which we are going to learn today is common emitter configuration, right? So in this common emitter means this emitter is common to the input signal and the output signal. This is the common ground here. So you are biasing this transistor with a base voltage. So this is required so that this transistor is not in the cutoff region, but it is more than 0.75, so that when you are applying few millivolt signal, it still remains on for the entire AC signal, right? If it is going from here to here, say if you say if you are biasing it at 0.8 volt, then when it is going up, it will go to 0.81, and when it is coming down, it will come to 0.79. So it continuously, this diode is on. Otherwise, you will have, it will start, if you don't give this bias voltage, and if it is 0, then you will find the negative cycle gets clipped, or till this signal comes to 0.7 volt, and there will be no change in current in the collector also. So those are the issues. So that is the reason we need to bias it properly. Okay, and then you have a load resistance connected here, and a voltage which is applied for reverse bias between the collector and base. So you have one more voltage. So this is known as the common emitter configuration. Now we will try to compute what would be the gain and things like that. Now this common emitter configuration can be realized using an NPN transistor or a PNP transistor also. When we do it with the PNP transistor, if you see, then the polarities of these voltages change. Now you got, this is N and P. If this needs to be on a forward biased, you need to give a negative voltage to the base with respect to the emitter, right? Again, this NP also, now if this has to be reverse biased, so now this P has to be given negative voltage with respect to this voltage. So you see the polarities here have got interchanged here. Now it was positive here, because you are using a PNP, negative and negative. So the functioning will exactly be the same, the AC analysis part and all. Only you just have to take care of the directions of the current the way it is represented here. Here if you see the emitter current, it is shown below, base is here, because this is showing the direction of the positive ions. So that is the reason this base current is from P, it's entering in, so it is pointing in here. From here it is from P, it is coming out to N, so you will find it is pointing outside. So this is the only difference. You can use either of them. Now if you see, this is the known as the input DC characterization of common emitter. That means here it is a forward biased diode. Okay, this is just a diode. Base emitter acts like a diode. So if you keep increasing VBE, after 0.7 volts, the current is going to rise exponentially, right? So we are going to bias it somewhere in between. So this is known as the DC input DC characteristics of a common emitter configuration, right? From the when we look for, this is known as the output DC. So if you change VCE, generally there should not be any change in the collector current. Okay, but if these are the plots, okay, for various VCEs. This is, see, the first one is almost horizontal. These are all almost horizontal lines. That means they are not changing. Okay, this is only changing with respect to the base current. So this is for IB is equal to 0. Now if IB is equal to 10 amperes, then you will find here it is close to 1 milliampere. That means for 10 ampere base current, you will find IC is 1 milliampere. So that means it is around beta is around 100 in this particular case. Okay, for again for 20 it is close to 250. Okay, so it is like this. Look, so the beta beta times IB is the current. Now you will find ideally this should be horizontal, but they are not horizontal. We will not get into the physics of this, but just remember that for an ideal transistor, any change in VC should not change the current, but there will be a small current variation. If you see, the current variation is not very large, so this is a small slope. Okay, it's not a big slope, there is a small slope. Okay, and that small slope, when we transform this into a small signal equivalent, we introduce an R0 which comes from this slope out here, right? Okay. Now this is how the amplification takes place. You give a small signal out here, right? So you give a small input signal that is going to change the IB. Now that change in IB is going to change beta times change in IC. Now that beta times IB change, IB is going to flow through this RC, right? So that is how we get a huge gain. If I go to in the next slide, and it is explained out here. Okay, this is like a emitter, common emitter configuration, where we are using two resistors to bias this above 0.75 volts, around close to 0.75 volts, and then you are giving a sinusoidal signal. We are using this coupling capacitor so that whatever DC voltage out here should not get coupled to the an AC source here. So this is kind of blocking the DC from entering into the source. So from the source the AC can come here, right? So here you will have the DC signal which DC bias, and over and above that you will find this small signal available here, right? Now this is the small signal equivalent of this circuit. So you have RB is nothing but for small signal we are going to ground all the DC sources. Okay, so now because we are only speaking about the change in voltage and change in current. Okay, so all those DC components which don't change with time, we have to ground them. So once we ground this, R1 and R2 become parallel, which is known as RB out here. Now this is the source resistance. Okay, this source may not be ideal, but there could be some source resistance, right? So that has been shown out here. And then we know the transistor in a small signal equivalent model, we replace it by R pi out here. And then this is instead of beta IB, it is given as GM V pi. Okay, certain textbooks follow this convention, and we'll see what is the relation between beta IB and GM V pi. Okay, so this is the IB is going to flow here, beta IB is going to flow here. Then you have this R0 here, that we said that comes from this particular slope, because this is not horizontal. The IC varies with little bit slightly with the change in VC. So that is the reason we have introduced this R0 out here, which will be close to in mega ohms. Okay, so for small approximations we can neglect that. And this is RC. This is the RC. Okay. This is the RC. Now since DC source we are going to ground it, so we have grounded it here, and the AC source coupling capacitors will get shorted for AC analysis, so that is not there. And this is the load resistance. And now GM V pi is nothing but beta IB. So GM is beta IB by V pi, right? So you can this is IB is nothing, V pi by IB is R pi, right? So you get R pi. So GM is nothing but beta R pi. Okay, so these two things are one and the same. Okay, now if you see V in is IB R pi, right? So if you are giving a voltage out here, the current that will flow here will be beta times RB. Now IC is beta times IB. Okay, this current is beta times IB. And what is going to be the output voltage? So you have these three resistances in parallel now. So so you have RS, R pi, and here also I am writing V in is equal to IB R pi. If this is the source voltage, if I consider RP is much greater than R pi, and RS is much lower than R pi, then I can assume this entire voltage is available here. Okay, so I write IB R pi, right? Otherwise, if you want to do an accurate analysis, then VS is available here, then this becomes parallel to each other. So you can use the potentiometer rule to compute what is going to be the voltage out here, right? So it will be VS into into RB parallel to R pi divided by RS. In the denominator you will have RS plus RB plus R pi. So you can do that, okay, if you want to get accurate results, but this is an approximation which is generally true for all real time systems. Okay, now if you see V out is again here also we are making some, this R0 is very large, and RC also we have to keep it larger than the load resistance. Okay, no, the load resistance has to be much larger than RC. Okay, then you get a V out is IC RC. Now if you gain is nothing but V out by V in. So if you divide that, you will get the gain as minus beta RC divided by R pi. Okay, so this negative sign symbolizes that the phase signals will be out of phase. Like if you increase the voltage here, more current will flow here. Okay, so the output voltage here will be VDD minus that much, right? So the signal will start dropping. The voltage here will start dropping out here. Similarly, when this signal is going negative, lesser current will flow here, and hence there will be lesser IR drop, and the signal level will go high. So you will find whatever signal we are observing here after the capacitor, it will be 180 degree out of phase than what you have applied here. So that is why this negative signifies out here, right? So if you see now, there are a few more things about properties of common emitter configuration. We should know this because depending on the application we have to decide what kind of amplifier we would want to use, whether common emitter, common base, or common collector. Okay, so so for that we need to know what is the properties of this common emitter. Now if you see here, the input resistance as seen from here is from the source side will be RB parallel to R pi, right? Okay, so you can say that this has got a fairly good high input impedance. Okay, so that is okay whenever we when the source, we don't want to draw any power from the source, and suppose you have one amplifier driving the other amplifier kind of thing. So this is okay. Okay, but sometimes in especially so in RF amplifiers and all, where suppose you have a low noise amplifier and you have some antenna which is picking up the energy from the air. So in that case you would want to match the input impedance of an antenna with the input impedance of the amplifier for maximum power transfer, right? We learnt about power transfer theorem. So maximum power transfer would happen only when the source impedance is matched with that of the load impedance. So now you can consider this whole amplifier as an load, and which is represented by the input impedance. So in those cases, like if you have an antenna of 50 ohms, this will offer very high input impedance. So whatever energy is being captured by the amplifier, by the antenna, doesn't get transferred to the amplifier. So in such cases this amplifier is not suited. So we need to look for an amplifier which has got low input impedance, because most of the antennas have got very low input impedance. Okay, they are of the order of 50 ohms. Mostly it is 50 ohms, 75 ohms. So in the RF domain you have antennas which are generally of 50 ohms. Okay, so this is not so this is it is a good thing, because it won't consume power when one amplifier is driving the other. So this can be the second stage of amplification, and in many cases, or in cases where input impedance of the source is high. Okay, so in those cases this is fine, but the only restriction is it has got a high impedance and a high input impedance. Okay, so that is one. So it is in a way you can say it is you can't clearly say it is good or bad. That depends on the application. So depending on the application you need to choose the correct amplifier. Okay, now this is another. If RB is much greater than R pi, you can approximate it to be R pi. Okay, and now the voltage gain we saw it is beta RC R0 RL, okay, by R pi. So again, if you consider an RB and RS, this gets modified like I discussed in the previous stage. So there is a voltage gain here. Okay, now there will be a current gain in this amplifier also, because beta current is flowing, IB is flowing here. Okay, and beta times IB is flowing here. So this amplifier provides current gain, it provides voltage gain, and it also provides a power gain. Okay, now where is that additional power coming from? So So see, if you see the input side, the voltage is less, current is less. Output side, the voltage is high, the current is high. Okay, so obviously the power, whatever VDD we are connecting it here, the power is being consumed from here. Okay, so there is an amplification of the power. Okay, power cannot be destroyed, right, or created, right? It has to get, if the load is taking more power than what the source is providing, then somebody has to give that power, additional power, and that is given by this VDD which is connected here. Okay, that gives the additional power. And if you see from the output resistance side, okay, now the output resistance is an RC parallel to R0. Okay, from here if you see RC parallel to, so this is also high resistance. Okay, so that is why this has gotten a high output resistance. For certain applications it is good, and for certain other applications it is bad again. Now if this amplifier is going to drive one more amplifier, then there is no problem with it. Okay, but suppose this is going to suppose I have to connect an headset. Okay, yes, a earphone of 5 ohms or 6 ohms. Okay, even the speaker amplifiers what we have, that will have only an impedance of 5 ohms. Now if you see the voltage gain equation, and now if RL is very low, the entire voltage gain drops, right? So now we have this amplifier works as long as RL is large. Okay, now the moment RL becomes very low, then this amplifier is not suitable, because you will find in the voltage gain equation RL is in the numerator, and the moment RL comes into it comes to 5 ohms, 10 ohms and all, then you will find the signal is getting attenuated. So this amplifier is not suitable where we need voltage gain and RL is very low. Okay, so these are some of the things which you should know. Okay, which will help you choose the correct amplifier configuration. So when we learn the other amplifiers also, then we will come to know, okay, in case RL is low, then what is the kind of amplifier which we need to choose. Okay, so that we will learn subsequently, right? Okay, now we saw that in the last class we saw that merely connecting R1 and R2, giving a bias voltage here, this particular transistor does not have a stable DC operating points. That means the IB will fluctuate a lot with the temperature in this particular configuration. Okay, IB is not immune to temperature variations and VDD variations, that we learnt in the last class, and we learnt that by putting an RE here it becomes pretty stable. So this is a stable biasing circuit. Okay, here this is the best way to bias an BJT, where you have an RE also. So if you learn from the previous class, by putting an RE here, you have 1 plus beta RE coming in the denominator for delta IB with respect to delta VD and delta VBE. So you will find this circuit is pretty stable to temperature variations and VDD variations. Okay, power supply fluctuations. So it is immune to that. So that is the reason we put an RE here. Now by putting RE, what happens? Now the voltage in the small signal, if you see, now Vin will become, okay, Vin which is applied here, this will be R pi into IB, and then you have an IE into RE. Okay, now IE can be written as 1 plus beta times an IB, and then you take IB common here. Okay, so this becomes like this. So now IB is Vin divided by R pi plus 1 pi beta RE, and output voltage, it remains like an ICRC, right? If we are assuming RL to be much and R0 much higher to RC, like in the previous case. So if you do that, so it will be the gain will be RC divided by, okay, beta RC divided by 1 plus beta, this entire thing, right? Now if you approximate this whole thing as beta RE, then the voltage gain will become RC divided by RE. Okay, you can divide this on the numerator. Output voltage will be V out will be beta IB RC, right? So if you divide these things by V in, in the denominator you will have r pi plus 1 plus beta Re. Now I neglect this r pi, and also 1 plus beta I just put it as beta, because beta is 200. So instead of 201, if I write 200, nothing happens. So in the it's going to make negligible effect. So in the numerator you have beta Rc, in the denominator you will have beta Re. So beta goes, and you have minus Rc by Re. Now if you see, the gain has reduced here in this particular case by putting this Re. Okay. You will see you will not get a gain of 100 or 200 in this particular configuration. It is possible to get a gain of 10, 20. Okay, so that is the maximum gain. So this is the penalty you pay for stability here. And now one advantage out here is if you require high input impedance for some reason, then the input impedance is increased in this particular case. If you see here, V in is IB into R pi plus, so V in by IB is the input impedance, right? So you get R pi plus 1 plus beta. So for certain applications where you require high input resistance, okay, so then you can use this. Okay, again, this also output resistance also gets modified accordingly. Now if you want a stable DC operating points, but you want an AC high gain, okay, so this is very widely used circuit, which is known as common-emitter, and this is an you will find it has got large applications. Even a similar circuit in CMOS technology also, which is known as the common source amplifier, that is also used in most of the state of art op amps. Okay, here also this also becomes part of the op amps, because this is, if you see here, it is got in the DC analysis everything remains same. Okay, whereas in the AC analysis this capacitor is going to short this Re. Okay, for the DC analysis again, and this R1, R2 and Re will be there. When we do DC analysis, we open circuit the capacitor, so you will find okay, it is stable. Okay, so whereas for AC analysis we short these resistance out here, and then if you see, once we short this resistance, again you will get back the gain as beta Rc by R pi, right? It is the common-emitter configuration without without the emitter resistance. This is the same original gain which can go up to 1000, right? So you will find you are getting high gain again, right? So the rest of the things again remains same as that of this configuration, right? So although this Re is there, okay, so by using a combination of Re and Ce, for DC stabilization Re would act, and for AC gain this capacitance will bypass this Re, right? So now, so this is how a common emitter configuration with bypassed emitter looks like and works. Okay, now suppose I want to make an amplifier out here. Okay, if I take a practical design example, suppose I have a 24 volt battery, I have a microphone which gives me 10 millivolt, and I have to drive a speaker of 8 ohms. Okay, so first and foremost, see it says 8 ohm speaker, so I can't use an CE amplifier finally to drive this load, but I need a gain of 100. Okay, it says I need a gain of 100. So let me now first design an CE amplifier, and subsequently we will see how to integrate this speaker onto that. So let me first target a gain of 100. Okay, so how to target this gain of 100? So this is an CE amplifier, so we need to find out the values of resistances, right? So how to compute these values of these resistances? First and foremost is we need to decide on how much current we can allow to flow here. Now it depends on many a time the power budget will be given. Like if you have a 24 volt battery and you want to operate this amplifier for a certain period of time, right? So that decides the power budget. Okay, so accordingly we select the current. Okay. Similarly, for various BJTs which you might have with you, so you will have to find, there will be a curve given between the value of beta with respect to the various currents will be given. Okay, now if I go back here, here if you see the here for a low current here, okay, it is around 150 and the it is 100 out, 10 out here. So beta comes to be around 150 here. Now if you go higher up here, if you see here, if you are going to have a beta, DC beta of 20, right, and if you see here here it is not even 150, less than 150, whereas here it is slightly higher if you see compute the beta. So you will have to target some beta value. Okay, so that can, for that using that target beta value, we decide on what is the collector current. Okay, so that depends on the specifications of the particular this. You have to see the data sheet and target the value, and you have to decide the value based on your power budget. Now here in this particular case, I have taken a 1 milliampere current which I am going to allow to flow in this transistor. Okay, so I have taken 1 milliampere. Now for during an DC steady state operation, what should be the voltage here? Now if I require maximum swing here, this voltage can go up to VDD, right, 24 volt, and what is it, it can come up to 0. So this should be ideally at 12, right? Okay, so I should put this around 12 volt, so that during the positive going cycle it can reach 24, and in the negative going cycle it can come to 0. But also you will find that this transistor, okay, when it can't reach 0 here, because there will be a 0.2 volt minimum which will be available in VCE. Similarly, for bias stabilization across RE, we generally drop 10% of VDD. Okay, that is how we make this transistor DC operating stable, right? So if it is 24 volt, we allow 2.4 volt across this RE and 0.2 volt here, right? So 2.4 plus 0.2, so total voltage which at this point, okay, it can swing from 24 to 2.6 volt. Okay, 2.4 plus 0.2, 2.6. Okay, so that is the range. So I will want to bias somewhere in between that. So I take 24 minus this divided by 1 milliampere, which is the current which is going to flow here, by 2. Okay, because 1 milliampere that is the voltage drop, 1 milliampere into this RC, that will be the drop here. Okay, so that is the reason I use this formula to compute the value of RC. Is it understood? 24, I want this voltage to be somewhere in between 24 and 2.6. okay, and RC is the so I have to drop that much voltage across RC. Half the voltage I need to drop across RC, and the current flowing through RC is 1 milliampere. So I can use this formula to compute the value of RC. Okay, once I have done that, now I know so approximately 10K, because you will find resistances of only certain values will be available, right? So 10K. So you will have to round off. I have probably explained you earlier what are the resistance values which will be available in the market. I think even 15K will not be available. You might have to use 14.7K, right? Okay. Now similarly RE. Now RE is, like we discussed, 10% of the VDD will be dropped across RE. So 2.4 divided by 1 milliampere. Actually the current in RE will be it is approximately equal to IC, right? So I am writing 1 milliampere here. So these are some rough hand calculations to quickly decide the values of these resistances, so that we allow these so that we design this amplifier and give an input signal and see the output signal. Okay, so I can compute the value of RES 2.2K. So these are all just certain rules and tricks which you can use. Now if you see what will be the voltage out here, the voltage out here will be 3.1 volt, because 0.8 volt here, if you are allowing this to be in the forward bias region. Okay, 0.8 plus this is 2.4. Okay, or 0.7 plus 2.4. okay, this comes to approximately 3.1 volt. Okay, now what would be the current through R2? Okay, now if you see IB, right, and IB is this is 1 milliampere, right? So this is 1 ampere collector current. So I need to have the IB will be IB, say if I take a beta value of 50 for n case, so now 1 milliampere divided by 50 will be the base current which is going to flow here, and I would want 10 times of IB to be flowing in this branch. Okay, is it understood? Let me explain it once again. Now IC, okay, IC is 1 milliampere, so 1 milliampere divided by 50 will be the base current which is flowing here, right, base current into this circuit. And for this circuit to be working stable, I want more current, 10 times the current to flow in this particular circuit, so that if there is an so this should offer for a small signal analysis, whenever there is an fluctuation, that should get absorbed here. Okay, so that is the reason I allow these resistances, okay, 10 times the IB flowing into these resistances, so that so I have to multiply that by 10. Okay, so the base current. Okay, so that is the reason I have put a factor of 10 here, right? So you can compute the value of R2 accordingly. Okay, so once you get R2, similarly if you have to compute an R1, so you can do that by, because this has become 21 because this voltage is now 24, so you can and this voltage is 3.1, so if you take a rough approximation, it gives to 21. So this is, you compute the value of the R1 to be 220, right? So now these capacitance, okay, generally what is this, these capacitances are decided, the values of these are depending on your frequency of operation. Like R and C together, they will act like an high pass filter, right? So depending on your frequency of application, okay, for whatever your desired frequency, they should bypass RC. So this is an high pass filter, right? So you have to, similarly this is also an high pass filter where high frequency will be coupled here. So the values of these capacitances depends on your frequency of operation, right? So now if you see here, if I have done an LT spice simulation, I have given a small signal here which is represented in the blue line. So it is almost negligible, so I am getting an output signal which is almost 100 times the signal, more than 100 times the input signal level. Okay, so this is just to give an idea how to design an CE amplifier. Okay, for this particular course you don't have to remember the design aspects. Okay, till here is good enough for you. Okay, why I have just put these slides to just to give you a rough idea about how practical circuits are implemented and what are the design rules which we need to use to implement these circuits. But you don't have to remember this for this particular electrical science course. Maybe when you do a microelectronics course or in the next semester, so then these things will be important. Okay, so thanks a lot now for today.